Generalized definitions of trigonometric functions. So far we have defined our trigonometric functions on the unit circle using x and y, so some point on that circle. But what if we are not on the unit circle? So if the point xy is specified by the angle t on the circumference of a circle with radius r, so no longer just assuming that that radius is 1, then we can define the 6 trigonometric functions as follows. So notice that we can still use x and y, the coordinates of that point, but now we also want to consider that we have to use r, so the radius of that circle. So let's draw a little picture just to say, what is this talking about? So now we are on a circle where the radius is r, not necessarily 1. And we still have some point xy here, and that is going to correspond to the terminal side of some angle t. All right, well, we always want our definitions, if we have some new definition that we're introducing, we want it to be compatible with everything we've learned thus far. So let's check this with the unit circle. We'll just check the cosine t and sine t. So on the unit circle, r is 1. So let's see if that works. So cosine of t gives me x over r, which is x over 1, which is x. And cosine of t is equal to x on the unit circle, so I'm feeling good about that. And I'm assuming that sine of t will work the same way. Sine of t is y over r, given this generalized definition. Okay, on the unit circle, right, because now we're saying unit circle, then I just get y. And sine of t is equal to y on the unit circle. So it's still compatible with what we know from the unit circle. What about right triangle trig? So let's look at right triangle trig. Okay, so we're on some circle of radius r, and I'll draw some point in the first quadrant, say here, and I'm saying this is xy, okay? And this is some angle t that's corresponding to that point, because the point is on the terminal side. And here is a right triangle that I have created. All right, well, because this point is x comma y, I know to get to that point, I'm going to be going over x units to the right and up y units to get there. So that gives me the lengths of those sides of the triangle. And with reference to angle t, this side is adjacent, the y side is the opposite, and of course the hypotenuse. Now this is the important part. We're just checking this with right triangle trig, and this is saying for any circle where r is the radius, so not necessarily 1. So we're going to write this as r instead of 1. All right, so let's see what we get here. So let's start with cosine. We'll say, well, cosine of t is equal to adjacent over hypotenuse, so x over r. Does that match the definition that we just gave? Yes, it does. Okay, excellent. Sine of t. All right, remember what we have SOHCAHTOA when we're in right triangle trig. So now we're here at sine. So sine of t is opposite over hypotenuse, so y over r. And that matches what we were just given up here. We can also do tan of t, and we know that is opposite over adjacent, so y over x. And again, I can see all of these match what we're given up there. So how can we use that? Well, let's say we're given that the point -3, 2 is on the terminal side of an angle theta in standard position. Determine the values of the 6 trig functions. So we really want to draw these out to be extra clear here. Okay, so I have some circle, and I don't know the radius, right? But they did tell me that -3, 2 is on the terminal side of some angle. So why don't I actually erase the circle first? I'll just draw the point. That might be a little easier. -3, 2. Okay, so here's my point, -3, 2, and I have it just in that second quadrant there. And then this could correspond to some circle with radius r. Okay, so what would that look like? Well, I could just kind of completely fill it in. And again, this is just a sketch so that I'm kind of using it so that I can use the definitions. I'm thinking of it on the circumference of a circle. So if that is the case, I know for my new definitions that we're just talking about now, I need x, y, and r. So I'm given x is -3, y is 2, but I still need r. So how can I think about r? Well, think about this triangle right here. Okay, I'm going to pull it out. Look at it over here. Okay, r is r. This is a right triangle. The short side would have a length of 2, and this long side, now I go to the left, right, to like kind of go over to this point location to get to -3, comma 2, but lengths of triangles, right, the measurement of those, sorry, the lengths of the sides need to be positive. So I can think of this as the absolute value of -3 gives me 3 for the length of that side. So now I can solve for r. So r squared is 3 squared plus 2 squared, given the Pythagorean theorem. So r squared is 9 and 4 is 13, so r is the square root of 13. So now I have r is root 13, and now I'm ready to find my 6 trig function values. All right, so let's see. I'm going to have cosine of t is x over r. So it's x over r, that's a reminder, and that's just -3 over root 13. Now I always want to rationalize the denominator, so negative root 3, 13 over 13. So not the prettiest value, but it'll work. Okay, let's do the same thing for sine of t. So sine of t is y over r, which is 2 over root 13. So this works the same way. We get 2 root 13 over 13. Okay, great. I might move down here to the bottom left corner. We're not out of room here. So tangent of t, what do we get there? Tangent of t is just y over x, and that's just 2 over -3. Oftentimes we want to just write that as, say, oops, in this case, -2/3, so we pull that negative out. All right. What about secant of t? Secant of t is just r over x instead of x over r, so that is root 13 over -3 would be negative root 13 over 3. Okay. Cosecant of t is just r over y, so root 13 over 2, nothing left to do there. And then cotan of t is just x over y, so -3 over 2, and that simplifies to just -3 halves.